Welcome to AI and Machine Learning Deep Dives. Today we're taking a deep dive into support vector regression, or SVR, a remarkably powerful technique for predicting continuous outcomes. Whether you're just starting your journey in machine learning or you're already, deeply immersed, we're going to unpack how this algorithm truly works, why it's so incredibly effective, and what makes it stand out in the bustling world of predictive modeling.
That's right. Our mission today is, well, quite clear. We want to illuminate the core concepts of SVR, explore its unique characteristics, and really demonstrate its efficiency, particularly when we put it side by side with more classical regression methods. You should walk away from this deep dive with a crystal clear understanding of SVR's strengths and, crucially, how to leverage them in your own work.
Okay, let's kick things off maybe with the basics. We often talk about regression as that fundamental statistical process for estimating relationships between variables, typically aiming to predict the dependent variable based on one or more independent ones. Classical regression, like linear regression, it tries to fit a precise line or curve to your data. But what happens when that data isn't perfectly clean, when it's like riddled with outliers, or when you're dealing with truly massive data sets? Traditional methods can sometimes stumble there, right?
That's a critical observation. Yeah. While classical methods are foundational, incredibly useful, they can indeed struggle significantly with large data sets. And they often show what we call poor tolerance for contaminated data, meaning they're just highly sensitive to outliers. They can really pull the entire model off course. This undeniable need for a more robust procedure, one that consistently yields more accurate, more reliable predictions, is precisely what spurred the development of techniques like robust regression and, well, more powerfully, what led us to support vector regression. It was really about finding a solution that didn't buckle under the pressure of, real-world data imperfections.
Okay, so if traditional methods are sensitive, what exactly is SVR doing differently? Most of us have probably heard of support vector machines, SVMs, right? Primarily used for classification, drawing clear boundaries to separate data points into different categories. Does SVR just got to port those ideas over to regression to numbers?
Well, what's truly fascinating here is how SVR cleverly adapts those core SVM principles. You're right. In classification, SVM aims to find a hyperplane, a fancy term for a decision boundary that optimally separates different classes of data. And it does this while maximizing the margin, which is the distance between that hyperplane and the closest data points from each class. The maximal margin classifier, we call it. SVR takes this core idea, the margins, the hyperplanes, but instead of separating classes, it uses them to predict continuous outputs. It's really more about containing the data rather than separating it.
Right, containing. And here's where it gets really interesting for me. Unlike traditional regression, which typically tries to minimize the sum of squared errors, basically punishing every single deviation from the predicted line, no matter how small, SVR introduces something, well, quite revolutionary, a margin of tolerance. We often see this symbolized by the Greek letter epsilon, SVR. This means SVR seeks to find a function or a best fit line or, a hyperplane in higher dimensions that deviates from the actual target values by a value no greater than this specified epsilon margin. And the goal is to make that function as flat as possible within that margin. It's a fundamental shift in how we define best fit, isn't it?
You've absolutely hit on a crucial distinction there, this epsilon insensitivity. It means that any errors within this defined margin are simply tolerated. They don't incur a penalty in the optimization process. So the core objective of SVR is kind of twofold. First, maximize the number of data points that actually fall within this margin of tolerance. And second, minimize the errors for any points that happen to fall outside it. Now, the data points that are closest to this margin, or perhaps even outside it, those are what we call support vectors. These are the critical observations, the ones that actually define the model. The more accurately these support vectors capture the underlying pattern, the more precisely our SVR model can explain the relationship in the data.
So what does this all mean for us, like, as practitioners? This distinct approach to error tolerance, it's a real game changer. That brings us to takeaway number one. SVR's unique approach to error tolerance, through its epsilon insensitivity margin, makes it exceptionally robust to noise and outliers in your data, giving it a significant edge over classical linear regression methods. Okay, moving on then. A concept that often comes up with both SVM and SVR is the kernel trick. For our listeners who might be familiar with this or maybe just hearing the term for the first time, what exactly is a kernel function and why is it so incredibly important for SVR's capabilities?
The kernel function. It's truly transformative in machine learning, I'd say. It's kind of the secret sauce that allows SVR to tackle complex, nonlinear relationships in your data. It does this by implicitly mapping your input features into a much higher dimensional space. Think of it like this. Imagine you have a messy, tangled string in 2 dimensions. Without actually untangling it, you lift it into a 3rd dimension. Suddenly, you can often draw a straight line or a flat plane to separate parts that were completely inseparable before. So in this new higher dimension, it often becomes possible to find a linear hyperplane that fits the data well, something that would have been absolutely impossible in the original lower dimension. And the genius of the kernel trick is that it performs this transformation implicitly. It avoids the huge computational costs that you'd normally face if you explicitly calculated all those higher dimensions. It's very clever.
So what you're saying is even if our original data looks completely nonlinear, maybe it curves or spirals or has really intricate patterns, the kernel lets SVR fit those complex relationships as if they were simple straight lines, just in a different higher plane. That's powerful stuff. And I know there are different types of kernels available, right? What are some common ones and how do we choose between them?
Exactly. You're spot on. Yeah, there are several types. The 4 main ones we commonly use are the linear kernel, polynomial, sigmoid, and the radial basis function, or RBF kernel.
The choice of kernel is absolutely crucial, really. It heavily depends on the underlying structure and complexity of your specific data. The RBF kernel, for instance, it's incredibly versatile and very widely popular in practical applications, mostly because it can handle a vast range of nonlinear patterns without requiring too much prior knowledge about your data's distribution. It's often a good default, the first one we try. Okay, so beyond the kernel function itself, I've definitely heard about other crucial parameters like C and gamma that significantly influence an SVR model's behavior. How do these parameters work? What kind of impact do they have on the model's performance?
Right, these are what we call critical hyperparameters, and they're essential for fine-tuning SVR to your specific dataset. You really need to pay attention to these. First, there's the C parameter. It's often called the regularization parameter. It basically controls the trade-off. The trade-off between achieving a low error on your training data versus keeping the model's complexity in check, trying not to overfit. A higher C value means the model has less tolerance for errors outside the epsilon margin. It forces the model to fit the training data much more closely, which can be great for minimizing training error, but it also carries a significant risk of overfitting, meaning it might not generalize well to new, unseen data. Then there's gamma. This one is particularly relevant for the nonlinear kernels like RBF, polynomial, and sigmoid. Gamma essentially defines how far the influence of a single training example reaches. Think of it like the reach or influence radius of each support vector. A low gamma value means a far reach, creating a smoother, broader decision boundary or regression surface. A high gamma value means a very close localized reach. This allows the model to conform very tightly to individual data points, which, again, can be excellent for capturing intricate patterns, but can also lead to pretty severe overfitting if you're not careful. It gets very wiggly.
It sounds like getting these parameters just right it's less about a magic formula and more about really understanding your data and the specific problem you're trying to solve. This flexibility in modeling complex relationships is clearly a huge advantage, though. That brings us nicely to takeaway number 2. SVR's ability to model nonlinear relationships through various kernel functions and its customizable hyperparameters like C and gamma provide immense flexibility and power, allowing it to adapt precisely to diverse and challenging datasets. Okay, so with all this theoretical power, how does SVR truly stack up against other regression methods when we're talking about real-world scenarios? Can you give us some practical examples of its performance? Did it really work better?
Absolutely. Yeah, we can look at a couple of insightful studies to illustrate this. For example, consider an experiment using the Hertzsprung-Russell diagram data for the star cluster CYG-OB1. Now, this data set had just a single predictor, but SVR actually significantly outperformed both simple linear regression LM and robust linear regression RLM. And RLM is already designed to be less sensitive to outliers. What was really telling was that even with 9 clear outlying observations in that dataset, SVR showed a much lower root mean squared error, the RMSE, and a considerably higher R-squared value, which indicates, a better fit and more accurate predictions overall.
That's compelling for a single predictor scenario.
Definitely.
But what about more complex data sets, say with multiple independent variables, like the prostate data set? I think that one has 8 predictors. How did SVR fare there?
The results were, remarkably consistent. With the prostate dataset, which also contained, I think, 9 known outliers, SVR once again exhibited the minimum RMSE and a greater R-squared when compared to both LM and RLM. What's particularly remarkable here, and it really speaks to SVR's stability, is that it performed efficiently and maintained similar predictive accuracy whether the dataset contained those contaminations, those outliers, or not. It's interesting, while visual fits for robust linear regression sometimes looked a bit better in simple scatter plots for single predictors, predictor data. The objective error metrics, the numbers, consistently favored SVR across the board. It truly shines when data isn't perfectly clean.
So it's not just theoretical hype then. SVR's efficiency and reliability are clearly demonstrated in practical applications, especially when dealing with those troublesome outliers or just really large data sets. That brings us to takeaway number 3. SVR consistently demonstrates superior robustness and predictive accuracy, particularly when dealing with data sets that are either large or contain significant outliers, consistently outperforming classical regression methods. Okay, this leads us to a pretty common point of confusion for many people, myself included sometimes. What's the fundamental difference between you using SVR with a linear kernel and just regular traditional linear regression? I mean, on the surface, they both seem to be aiming to fit a straight line. Why would I choose SVR with a linear kernel over good old linear regression if I'm just looking for a linear relationship?
That's an excellent question, and it's where the nuance truly lies. It's subtle but important. While both methods aim to model linear relationships, their underlying mathematical principles and, crucially, their optimization goals differ significantly. Standard linear regression, for instance, it minimizes the least squares error. It explicitly calculates weights, often through a direct formula, to find the single line that minimizes the sum of the squared distances from every single data point to that line. It's a direct, closed-form solution that finds a global minimum.
So it's really about trying to get as close as possible to all points, punishing any deviation no matter how small because it's squared.
Precisely. Every point counts, and counts quadratically in the error. Now, SVR, even when you're using a linear kernel, operates under a completely different philosophy. It sets up an optimization task. The goal is maximizing that margin of tolerance, the epsilon tube, while simultaneously minimizing errors only for points outside that margin. It typically uses more sophisticated iterative optimization techniques like gradient descent or quadratic programming to find this solution. So while linear regression aims for a precise fit to every point by minimizing its squared error, SVR explicitly prioritizes tolerance for errors within its epsilon margin and focuses its attention on those critical support vectors. This inherently makes it more robust to outliers, even in a technically linear context. And crucially, its whole architecture, the SVM framework, is designed for seamless extension to nonlinear problems just by swapping out the kernel. Traditional linear regression simply can't do that. It's stuck being linear.
That distinction is incredibly important then. It's not just about fitting a line. It's about how you fit that line and what you're prioritizing, minimizing all errors versus tolerating some and focusing on the boundary. And yeah, that inherent flexibility of SVR to easily jump to nonlinear problems just by changing the kernel. That's something traditional linear regression absolutely can't replicate. That brings us to takeaway number 4. Even with the linear kernel, SVR fundamentally differs from traditional linear regression by incorporating an explicit margin of tolerance and employing an optimization process that prioritizes generalized error minimization and margin maximization, making it inherently more flexible for nonlinear extensions. Okay, we've talked quite a bit about these critical parameters, C, epsilon, and gamma, along with, of course, the kernel choice itself. It seems like getting these right is absolutely paramount for good results. How important is it to really fine-tune these? And what are the best practices for doing so? Is it just a matter of, trial and error until something works?
Oh, it's absolutely critical for maximizing SVR's performance. And no, definitely not just trial and error. Well, not informed trial and error anyway. Pretty much every machine learning model, and SVR is no exception, has these parameters, these hyperparameters that need to be optimized. You need to set them to their best performing values for your specific data set. This systematic process is called hyperparameter tuning. And a very common, highly effective method for this, especially with SVR, is grid search cross-validation. It's kind of the gold standard approach.
All right, let me explain what grid search cross-validation is, just briefly, for those unfamiliar. It's a very methodical approach. It systematically tries out basically all combinations from a predefined grid of hyperparameter values that you specify. So you might say try these 5 C values, these 4 gamma values, and these 2 kernels. For each and every one of those combinations, it evaluates the model's performance using cross-validation. This means it intelligently splits your training data into multiple folds, say 5 or 10. It trains the model on maybe 4 of the folds, and then rigorously tests it on the remaining 1 fold that the model hasn't seen yet. It repeats this process, rotating which fold is held out for testing. This ensures that the model's performance evaluation isn't just a fluke based on one specific split of your data, but that it actually generalizes well. This systematic exploration helps you find the combination of hyperparameters that yields the very best average performance across all those folds, effectively preventing overfitting and ensuring your model is robust.
Exactly. And we've seen this in practice time and time again. When we apply thorough hyperparameter tuning, like using grid search cross-validation, to an SVR model, we almost invariably see a significant improvement. Better performance metrics like lower RMSE, higher R squared, compared to just using a base model with default parameters. It powerfully demonstrates why finding that optimal set of parameters for your specific data set isn't just a nice to have. It's really essential for unlocking SVR's full potential. It can be the difference between a model that's okay and one that's truly great.
Yeah, it's clear then that careful tuning can really transform an SVR model from merely good to potentially exceptional for your problem. That brings us to our final point, takeaway number 5. Effective hyperparameter tuning using methods like grid search cross-validation is crucial for optimizing SVR models, allowing them to achieve their best possible performance by finding the ideal balance between model complexity and error minimization. All right, so let's quickly recap our deep dive into support vector regression and just pull together the core insights we've discussed.
Okay. First, takeaway number 1 underscored SVR's unique approach to error tolerance through its epsilon insensitivity, highlighting its superior robustness to noise and outliers in your data. Really key.
Second, takeaway number 2 emphasized the immense power and flexibility of SVR. This comes from its versatile kernel functions and those adjustable hyperparameters like C and gamma, enabling it to model both simple linear and really complex nonlinear relationships.
Third, takeaway number 3 demonstrated SVR's consistent, superior robustness and predictive accuracy, especially when you're tackling challenging data sets, maybe those containing outliers or just a large number of observations. It frequently outperforms classical regression methods in those scenarios.
Fourth, takeaway number 4 clarified that crucial distinction. SVR, even when using a linear kernel, is fundamentally different from traditional linear regression. It prioritizes that margin of tolerance and uses a more general optimization approach, setting it apart and preparing it for nonlinear challenges right out of the box.
And finally, takeaway number 5 underlined the critical importance of effective hyperparameter tuning. Using methods like grid search cross-validation is really the key to unlocking SVR's full potential and achieving optimal model performance for your task.
What's truly fascinating here, I think, is how SVR, by intelligently extending these powerful principles from support vector machines, provides such a versatile, robust, and often indispensable tool for predictive analytics. We see it across an incredibly diverse range of fields, from financial forecasting and complex engineering problems to diagnostics and healthcare. It's really more than just another algorithm. It feels like a sophisticated framework for effectively modeling continuous data, regardless of its underlying complexity or, importantly, its imperfections.
Yeah, and this raises an interesting question, maybe a final thought for all of us working with data. Given SVR's remarkable ability to handle complex relationships and its inherent robustness to outliers, how might this change our very approach to data collection and, the initial cleaning steps we often obsess over? Perhaps it encourages us to shift the emphasis somewhat, maybe moving away from striving for perfectly pristine data, which is often impossible anyway, towards embracing more robust and adaptable modeling techniques like SVR right from the outset. Something to ponder as you approach your next predictive challenge, I think.
That's all for now, folks. Please like, share, and subscribe for more like this.